Okay, so let's start. Today we're actually going to do what we were waiting for this whole lectures, and we're going to actually create something that looks like Bitcoin, a decentralized ledger. So last time we talked about a centralized ledger. We saw how we can have a network where people can use their public keys as their identities, and they can also do transactions and everything. We saw the problem of double spending. We saw how we can solve double spending by having a blockchain. But then the problem was that I had a central bank, and the central bank decided what gets added to the blockchain. So now homework 1 is already out there, and you can see it. Actually, one of the questions in that homework is for you to decide what exactly can the central bank do in that centralized system. So how can the central bank really misuse its powers? But as far as the protocol is concerned, what could the central bank do? So in the centralized system, the central bank could do two things that others could not. Right? So this was the source of all the power that we gave to the central bank. One was that the central bank could actually create all the blocks. Right? So even though we had some limits on what the blocks could contain, we said that the blocks can only contain valid transactions. And of course, that means if you want to spend someone's money, you need their signature. But at the end of the day, it was the central bank who created all the blocks. Or to be more specific, instead of saying that it created all the blocks, I can say it's only the central bank who could extend the blockchain, because we saw that the central bank could also not erase the history. So it was committing to the history of the blockchain, and it could only add new blocks that were added to the end of the blockchain. So the central bank was the only one who could extend the blockchain. And I'm very lazy especially when it comes to writing, so I'm not going to write blockchain anymore. Whenever I say chain in this course, I mean blockchain. We don't have a chain of anything else. Okay, so the central bank was the only one who could extend the chain. But also we saw that the central bank was in control when it came to creating new units of currency. So when we wanted to answer the question of where does money come from in the first place in this system, we said that the central bank can create transactions that actually increase the amount of available money. So the central bank could print money. Let's write it like that. But by printing money, I basically mean it could create valid transactions such that the sum of outputs in these transactions were actually more than the sum of inputs. Now, we don't like central entities. Generally, two things you have to learn in this course is, first of all, we don't trust anyone. So everything should be trustless. We assume that anyone who can use any part of the protocol to do something wrong will definitely do that. So we don't want to trust anyone. And the second thing is we hate centralization. We don't want anyone to have powers that are not given to anyone else. So ideally, I want to have a network where all the nodes on this network are equal. So they have the exact same permissions. So if I have a central bank who can extend the chain, when I want to decentralize the system, everyone should be able to extend the chain. Of course, with some conditions. But the condition cannot be that you have to be a specific person. So anyone who does the same protocol, who does the same kind of steps, should be able to get the same results. And also, everyone should be able to print money. So let's just write this definition of decentralization here. So the definition that I'm going to use for decentralization right now, and we will later see that actually this definition is not great. But for now, the definition is that every node on the network has the same permissions. Okay. But of course, this doesn't mean that every node in the network behaves the same. People have free will, they can decide what they want to do. It's just that they have the same permissions. Okay. So now I have to answer the question of how to extend the chain. So how to extend the chain. And remember, the most important thing about the chain was that everyone should have consensus about the chain. So we had situations before where different nodes in the network had heard about different transactions, but that didn't matter because we said the transaction is done only when it's on the chain. And then we wanted to make sure that everyone has the same view of the chain. Everyone reaches a consensus about the chain. So when I ask how to extend the chain, I actually mean how to extend the chain while preserving consensus. Now, I have to add one more point here. Of course, if you are, let's say, a rogue actor on this network, so let's say you're connected to the Bitcoin network, but you're not following the protocol. There's no way I can force you to reach consensus with others, right? So I can always say, I think this is the Bitcoin blockchain, even though no one else agrees with me. But no one cares about that. So actually, the question needs another qualifier. And I'm going to ask how to extend the chain while preserving consensus for honest participants or honest nodes. So the idea is that I want to give you a protocol, and if you honestly follow this protocol, you will reach a consensus with all the other honest people about the stuff that is on the chain, right? So the chain is what we want to have consensus on. I cannot make sure that dishonest people reach consensus, but I want to make sure that at least my honest nodes are going to reach a consensus. Okay. So in Bitcoin, we actually call this process of extending the chain mining, and you will very soon see why it's called mining. But for now, I'm just going to say that extending the chain is called mining. And anyone who tries to extend the chain is called a miner. Miner with an E, not with an O. And so we have decentralization, so anyone can be a miner. You can be a miner on this network and you can start mining. Okay, but we have to say how we actually do the mining. So here's the problem. Let's say that I have a chain at some point. So this is my chain. It starts with block 0, and then there's block 1, which points to block 0. And then there's block 2, and so on. And let's say that I have a chain that goes until block n-1. And now I said everyone should be able to try to extend the chain. So maybe I have many different people on my network who are creating new blocks, and they're all proposing these new blocks to be added to the end of the chain. So I have a situation like this. Someone is proposing this block as block n. Someone is proposing another block. I might have many of these. I don't know how many I have. And I somehow have to figure out a way so that the entire network just chooses one of these proposals as the actual block that gets added to the end of the chain. Now, at this point, I don't really care about fairness. All I care about is consensus. I just want to make sure that everyone on the network agrees. Okay. So how can I do this? Well, the solution, the really kind of genius solution in Bitcoin is that we ask people to solve a really hard puzzle, and the first person to solve that puzzle gets to add the block. Okay. So if I have 3 different miners here who want to add their blocks, the first one who can solve the puzzle can add the block. And this is what we call proof of work. So the simple idea in proof of work is that we have a really hard mathematical puzzle, and I know that really hard is not really well defined, but I will define it soon. So I have a really hard mathematical puzzle. And I want to say that the first person who solves this puzzle or this problem gets to add the block. Person to solve adds the next block. Okay. Now, if I want to have a situation like this, what kind of a puzzle should I have? Well, of course, I want my puzzle to be really hard in the sense that I don't want to have a situation where two people solve the puzzle at the same time and then I lose consensus because there are two solutions going around the network, right? So really hard means really, really hard. And then when someone solves the puzzle, they have to somehow be able to prove to others that they have solved the puzzle, right? And others should be able to verify that the puzzle is solved, and the verification should be easy. So generally, whenever I'm talking about the word puzzle, what I mean is a computational or mathematical problem where solving the problem is hard, but verifying that someone else has solved the problem is actually easy. Okay, that's the property that I want here. So hard to solve and easy to verify. But I also need one more property. So suppose that I have solved the puzzle. How am I going to tell everyone else that I've solved the puzzle? So all of our communication was using this gossip protocol that we talked about last time. So if I solve the puzzle, I'm going to have my block and then the proof that I have solved the puzzle. And I'm going to just tell this to all of my neighbors in the network. And then I hope that they will say it to all of their neighbors and so on, and it gets propagated and everyone hears about it. But the solution should be unique to me. It should be such that no one else can actually steal my solution. Because of course, if I just tell my solution to my neighbor in the network and then the neighbor can say, this is my own solution, then they can mine it. And I don't want to do that. So I want to have a really hard mathematical puzzle that is hard to solve, easy to verify, and basically impossible to steal. This is the kind of mathematical puzzle. And now we go back to our cryptographic primitives and we think about some of the problems that we saw were already hard. And specifically, I'm going to use a cryptographic hash function. So remember, we actually had this idea of cryptographic hash functions, and we said that if I have some piece of data, it's actually quite easy to compute the hash of the data, right? But it's almost impossible to invert a hash function. So if I give you some hash value and I ask you to give me some data that has this hash value, you should not be able to compute that. So we have this kind of hard and easy dichotomy there. And now I just have to make sure that I design it in a way that makes it impossible to steal. So let's just look at how a block looks like. And I'm going to change the contents of my block a little bit. So I'm going to create a hash-based proof of work. And my laziness continues. So POW is proof of work. We will at some point see proof of stake, which is POS. But for now, we're going to just talk about proof of work. So what is a block? Let's just look at the structure of a block. If I have a block, what does it contain? So let's say this is my block. Of course, every block has a number. For example, this one is saying I'm block number 0. This one says I'm block number 1. And all of these are claiming that they're block number n. So a block has a number. But it also has a pointer to the previous block. And of course, we expect that it points to a block whose number is 1 less than the number of the current block. But I don't care about that too much. It's just I have a pointer to the previous block. I'm going to call it prev b. This is a hash pointer that points to the previous block. Okay. Now, every block also, as we said before, has a bunch of transactions in it. And we said that the way we encode the transactions is using a Merkle tree. So actually, this block should also contain a pointer to the Merkle tree. And we saw that the pointer to the Merkle tree is basically the hash saved at the root of a Merkle tree. Okay, so I'm just going to call this one transactions. And again, the details, the fact that my transactions are actually saved in a Merkle tree are not that important. The important point is that I have my transactions somewhere, and my block should have a hash pointer to my transactions. Okay, so this is a hash pointer that points to a Merkle tree of transactions. So I have maybe a Merkle tree like this. And no, actually a Merkle tree, the pointers were like this. Every node had pointers to its children. So each one of the leaves are my transactions. So let's say this is my transaction 1, transaction 2, transaction 3. And we saw that basically I saved the hash of transaction 1 here, the hash of transaction 2 here, and then I hash both of these things and put the hash here and so on. So I will have a hash at the root of my Merkle tree. And so my block has my transactions in it. And again, this is just the details of how it's implemented. What I care about is the property that if I change any of these things, my block will also change. So if I, for example, change my previous block, then this block also changes. Right? And if I change any of my transactions, for example, if I change this transaction, then all the hashes of the tree will change. So the entry in the block will also change. So I have this kind of immutability, which is if I make any changes anywhere, my entire block is completely changing. Okay. Now I'm going to add one more entry in my block. And actually, this is very much simplified. Bitcoin blocks have many more stuff in them. They have like timestamps and so on. I don't care about those. I'm going to also add a nonce to every block. And the idea here is that this nonce is just a number, and it's a number that is chosen by the miner who's creating this block. Okay. So this nonce is chosen by the block's creator or by the miner. Okay. Now, I did all of this because I want to set up a proof of work. I want to set up a puzzle. And here's the puzzle that I want to set up. I want to say if you want to add a block, you have to make sure that the hash of your block is a small number. Okay, so let's say this is the block B. I say for B to be valid, the hash of B, and let's say I'm using some standard hash function. Again, I don't care what hash function you choose, but everyone on the network should use the same hash function. So let's say I'm using a hash function that has 256 bits in its output. I say for B to be valid, the hash of B should start, let's say, with I don't know, 10 zeros. Okay, so when I hash it as a number, this number should be small. Okay, so the hash of B should be small. So for example, I can say hash of B should be of this format. Well, of course, I'm talking in binary. It should start with a lot of zeros. And maybe I say that I should have at least some number of zeros. I don't know. Maybe I should say I have at least 60 zeros and then something else. Okay. Now, if I do this, then I'm really setting up a hard problem, right? Because if someone wants to create a block, if someone wants to create a valid block now, they have to choose their nonce so that the hash of the entire thing. So when I'm hashing the entire block. Everything is hashed, right? The hash of this entire thing should be a small number. Now, as a miner, as someone who has created this block, I have control over all of these previous things. Of course, I can set the pointer to the previous block, and of course, I set it to the last block that I have in my own copy of the blockchain. I know the number of the block, but I get to choose the transactions that are put in my block, because I'm basically taking the role of the central bank, and the central bank could choose which transactions to put in each block. So as a miner, I choose a bunch of transactions, I create a Merkle tree, and then I can create all the blue parts of this block. But then for my block to be valid, I have to somehow choose this nonce so that the hash of the entire block is a small number. But I don't know how to invert a hash function. So what can I do? Well, this is actually the property that we have in hash functions, and I didn't talk about. I told you there is another property called puzzle friendliness that we will get back to, and this is where I'm using puzzle friendliness. Basically, the idea is that as a miner, my only option here is to just keep trying different random nonces, right? Because I have no control over the hash function, I cannot invert it, so I can just randomly choose a nonce, take the hash of the entire block, and see if the resulting hash is small enough, right? And if it's not, then bad luck. I'll just choose another nonce. And then I have to keep doing that until I find a nonce that has a small hash. So now, as you see, it's actually a really hard puzzle in the sense that, well, I have to just keep computing more and more hashes, and that needs a lot of computational power. And actually, the hash rates right now on Bitcoin are crazy. I don't remember how much they are, but it's like an amazing amount of hashes. You can never find a block using your laptop or anything like that these days. Okay, so we will have a whole different lecture on that. But for now, I'm just talking about the fact that solving this problem is hard, because in order to solve it, the only option I have is to try different nonces. And again, this is an assumption in my hash function. So a hash function is puzzle friendly if the only way we can do this is by trying random nonces. Okay, so I have zero information about my hash function. I have to constantly keep trying random nonces. But if I'm lucky, and if I actually find a solution, then it's very easy for others to verify my solution, right? Because if I find a block and my block has a nonce so that the hash of the entire block is small, I can just publish this block, and anyone else who sees this block can just take the hash of the block and verify that the hash is actually small, right? So I have these two properties. It's a puzzle, and my puzzle now, so basically in proof of work, my puzzle is kind of like inverting a hash function. It's not exactly inverting the hash function for one value, it's inverting the hash function so that the hash value is actually small. But anyway, this is my mathematical puzzle. It's hard to solve, you can think that if this hash function is similar to a random function, to a uniform random function, then every time that I choose a nonce, if I need to have 60 zeros, I have 1/2 to the power of 60 chance of actually getting it, right? Of course, our hash functions are not randomized, but assuming that they have a behavior that is random enough, then we have the same properties here. Again, I'm doing a lot of hand wavy things because I don't want to teach you cryptography. I want to teach you cryptocurrencies. But yeah, so you can think that if I choose this nonce randomly, I have to, on average, try 2 to the power of 60 nonces before I can create one block. Whereas when I create this block and I give it to you, you can just hash it and you can verify that the hash is small. So you can check in constant time that my block is actually a valid block. So it has both of these properties. It's hard to solve, it's easy to verify. And also, I want to say it's impossible to steal. Well, if I create a block like this, if you change any part of this block, then you're changing the entire hash. So when I find a valid block, every information in this block is basically hard-coded. No one can change the number, no one can change the pointer to the previous block, no one can change the transactions. Right? If you change any of these things, then the hash of the entire block will change, and then the same nonce will not work anymore. So no one can steal my block. If I create a block like this, I am sure that if I just give it to my neighbor, the neighbor cannot change it. The neighbor can just send the same block to others. So we can have a propagation, but there is no stealing of the solution. Okay. Now, so finally, we have kind of a working protocol, and this is how our protocol works. So first of all, we say that every node is equal. And this is our decentralization. So every node has the same permission as every other node. Okay. Now, what can my nodes do? Since everyone is equal, everyone can do everything that we had in the previous centralized ledger. So everyone can basically be a transactor, which means they can create new transactions. Everyone is a node on the network. And everyone can be a miner. And miner means that it's someone who creates a new block. Okay. Everyone can, but not everyone has to. So if you're on the network, you can basically wear any of these 3 hats as you like. You can transact with the money. You can just be a node on the network and pass messages. Or you can be a miner who creates new blocks. So we have 3 roles, but anyone can choose which subset of these roles to have. Okay. Now, how does a transactor work if I want to create a new transaction? This is exactly like the previous case. So from the point of view of a transactor, everything is just like a centralized ledger. If I want to transfer some money to you, I will just create a valid transaction that sends that money to you, and I sign it, and I just give it to my neighbors. And then I wait for it to be added to the blockchain. Okay? So transactors, this is, they're going to be exactly as in the centralized ledger. Okay, what does a node on the network do? Well, this is also very similar to the case of the centralized ledger. So as a node on the network, I just listen for transactions and blocks. Whenever I hear a new transaction, I check if the transaction is valid. And the conditions for the validity of a transaction are also the same as the previous case. And if this transaction is valid, I just give it to all of my neighbors. That's it. And when I hear a block, I do the same thing. I check if this block is valid. And if the block is valid, I add it to my blockchain, and I also propagate it to all of my neighbors. If the block is invalid, I just discard it. The only difference here is that the validity of a block has a new condition now. So previously, I had these conditions that in order for a block to be valid, it had to have the signature of the central bank. And of course, it also had to only have valid transactions inside it. So now I'm not going to change the part about valid transactions. Of course, I'm not going to allow invalid transactions in my blockchain. But I'm going to say, instead of having the signature of the central bank, my block should have a small hash. Right? So the condition on the validity of a block changes. Okay? So we will talk about this a little bit more. And what does a miner do? A miner just does everything that the central bank did. So a miner creates a block. But other than creating a block, it has to also find this nonce in the block. So the miner has to solve the proof of work puzzle. So this miner does everything that the central bank did, but it also solves proof of work. And if it finds a valid solution to the proof of work problem, it just publishes it. Okay. Now, actually, I could easily explain to you what a transactor does and what a miner does. I have to talk a little bit more about what the nodes do, because this is going to change a little bit. So I have to again look at the viewpoint of nodes. Okay, as a node on the blockchain, if I hear a transaction, what am I going to do? I'm going to do basically the same thing that I did before. I'm just going to check if this transaction is valid. And if it's invalid, I'm not going to propagate it anymore. But actually, I'm going to change that check a little bit. Okay, so if the node hears a new transaction. Okay. Before that, actually, let's say, what do I save as a node? As a node, what am I keeping track of? So previously, we said that the nodes keep track of the blockchain, but now I'm going to keep track of two things. So a node keeps track of two things. And I'm going to call them, one of them is the blockchain. The other one is what I'm going to call the mempool. Okay. Now, you all know what the blockchain is at this point. If I'm a node, my mempool is basically the set of all the valid transactions that I've seen until now, but are not yet added to the blockchain. So these are the transactions that I'm aware of. I know that these transactions are somehow happening. They're being propagated in the network. But I also know that these transactions are not finalized yet. They're not yet added to the blockchain. So I just keep track of these as well. Now, we have consensus only about the blockchain. So every node might have a different mempool. That's fine. A transaction that is in the mempool is not actually finalized yet. So if I hear a new transaction, what do I do? First, I verify the validity of this transaction. Okay, what were the conditions of validity? I have to verify the signatures, right? So I have to make sure that if the transaction is using your money, it actually has your signature. That's fine. I have to verify that the transaction is not creating new units of currency. So this was that famous two sums thing. So the sum of all the inputs to the transaction should be greater than or equal to the sum of all the outputs. And I have to verify that there is no double spending. Okay, so no double spending. Which means I have to make sure that this transaction is not using some money that was previously used in a different transaction. It's not using a coin or an output that was previously used in another transaction. But now previously I said that I just check for double spending with respect to the blockchain. Now I'm going to say no double spending with respect to the blockchain and the mempool. So the union of the two. So the idea here is that, let's say I'm a node and I hear that Alice is sending some money to Bob. And I propagate this transaction to others. And then later on, that first transaction is not yet on the blockchain, but I hear that Alice is sending the same money to Carol. Okay, so what do I know? I know for sure that Alice is trying to cheat. Alice is trying to do double spending. So what are my choices? I can either say this is not yet on the blockchain, so I'm just going to propagate it and eventually only one of the two transactions get on the blockchain. Or I can actually say, okay, Alice is cheating here. Let's punish her. Let's not propagate her second transaction. Right? So this is the choice that we're making. We're saying, if I see some transaction that is double spending with respect to another transaction that is in my mempool, not in the blockchain, I'm still going to say this transaction is invalid. And this is just to reduce the traffic on the network. Because if I don't have this condition, then I can easily do a denial of service attack. I can say, let's say I have 1 Bitcoin. I create 10,000 different transactions that are spending this 1 Bitcoin in 10,000 different ways. Right? And then if I want to propagate this, and if people only look at the transactions that are on the blockchain, all 10,000 of my transactions have to be propagated, and then that's a successful denial of service attack. So I don't want that to happen. So just to avoid that, I say if there is double spending with respect to my mempool, I also say this transaction is invalid. Now, if the transaction is valid, if TX is valid, what am I going to do? Well, I'm going to do two things basically. I'm going to, of course, add it to my mempool. So add TX to mempool. And I'm also going to propagate it. So I'm going to send it to all of my neighbors in the network, anyone else that is connected to me in the network. So send TX to all neighbors. Okay, this is when I hear a new transaction. Now, what happens if I hear a new block? If the node hears a new block B. Well, I have to first of all make sure that this is a valid block. How do I make sure it's a valid block? I have to see that it has a small hash and that it only has valid transactions in it. Okay. And of course, I wanted to point to the last block that I have seen before as well. So first, I verify the validity of B, which means I check that the hash of B is small. And by small, I mean that it has to be smaller than some threshold T, let's say, or let's call it D. It's smaller than some constant D. Let's say I have a constant in my system, and I only accept blocks that have a hash that is smaller than this value D. I will talk about how to choose this later. For now, I just want to say I accept it if creating this block was hard enough, if the person, the miner who actually created this block, put in the effort, had to solve the proof of work. Okay, I have to also check that all transactions in this new block B are valid. Now, this time, I want my transactions to be valid only with respect to the blockchain, not with respect to my mempool. Because remember, my mempool are transactions that I have seen but are not finalized. So it might be that, again, I have someone who's double spending and they created two different transactions, and one of those transactions is in my mempool. But then maybe the miner saw the other transaction first. And maybe the miner is adding the other transaction to their block and to the blockchain. So that's a valid thing to do. I'm going to allow that to happen. So I'm going to say that all transactions in B are valid. And of course, validity here means that they have the correct signatures and they're not creating new units of money. Sum of all the inputs is greater than or equal to the sum of all the outputs. And it also means no double spending. But when I'm saying no double spending, I'm only considering the transactions that are in the blockchain. And of course, the transactions in the block B itself. So because I'm definitely not going to allow someone to have two transactions that double spend the same amount of money, the same coin, even if they appear in the same block, because we don't want to have double spending. Okay. And now if it passes this check, if the block is valid, I do two things. I add it to the blockchain. Well, actually, I do three things now that I think about it. So I have my own copy of the blockchain. I saw this new valid block. I add it to the end of my blockchain, so I extend my blockchain. I have to also update my mempool. So I add it to the blockchain. I update my mempool. Now, again, remember, the mempool is just something that I have as a node. The blockchain is something that is shared with everyone. Everyone has consensus about. So the mempool was supposed to temporarily hold the transactions that are not yet added to the blockchain. So at this point, I'm adding a new block to the blockchain. So any transaction that is in that block should no longer remain in my mempool. It's now in the blockchain, right? And also any transaction that had a conflict with a transaction that is in the blockchain now. So if, again, I have double spending, maybe I have a transaction in my mempool that is doing double spending with some transaction that is now added to the blockchain. Then the transaction in my mempool is invalid because we said that only the transactions that are on the blockchain are finalized. So I have a finalized transaction that is conflicting with my non-finalized transaction in my mempool. I just remove the non-finalized transaction and I throw it out. Okay, so I do these things. And of course, I have to also propagate the whole thing. So I have to send my block B to all neighbors. So, and again, updating the mempool is to remove the transactions that are in B because they're now on the blockchain, and also remove transactions that have conflicts with B, in conflict with B. And by conflict, I just mean double spending. Okay. Now it seems like everything is working, but we actually need a little bit more detail here. So let's see what happens. I have an initial block. And let's say that the first block was actually set by the protocol, and this is B0. Sometimes they call it the genesis block. Okay, so we said in our protocol that this is the very first block. Now people keep adding blocks. So now we saw that if I want to extend the chain, I cannot just propose any block. I have to first solve the proof of work problem to propose a block. Okay, so let's say someone successfully added B1. And then someone successfully added B2. And this went on until we have Bn minus 1. Now, when I want to add the next block, everyone is competing. All the miners are competing. They're all computing these hashes and trying to find the valid block sooner than everyone else. And now we said that the problem is hard. So we hope that no two miners find the solution at the same time, right? My hope is that as the miners are doing this random process of just trying different nonces, no two of them will find the solution at the same time. So I'm hoping that only one solution will be found, and then that solution will be propagated, and everyone will see that solution, and everyone will extend their blockchain in the same way so that everyone has the same new extended blockchain now. But I have no mathematical proof for that. It might be that I get unlucky. Maybe two miners find valid solutions at the same time, right? Or at approximately the same time. So it might be that I have two different blocks here. Let's call it Bn and Bn prime. And it doesn't have to be two. It can be even more than two. And let's say that I was just unlucky and two different miners found valid blocks at approximately the same time. So what happens if two valid blocks are found at approximately the same time? Now you see, we have a problem similar to the initial double spending problem that we had before we even had a blockchain, right? These two blocks are found at approximately the same time. So the miner of the first block announces it on the network. The miner of the second block also announces it on the network. And then the nodes just keep verifying, and both of these blocks are valid. So both of these blocks will be propagated. But the problem is that the part of the network that sees this block first thinks that this is valid, and then this one is invalid because it's not adding to the end of the chain. And the part of the network that sees this one thinks this one is valid. So this is what we call a fork. This whole situation is called a fork. So I temporarily have two different valid blockchains. And my nodes on the network actually don't agree on which one is the valid one. So they have two different views. Now, of course, I cannot let this stand, because if I let it be like this, then it might happen that 10 blocks in the future, I again have another fork and so on. And we will have a situation where, again, we don't really have consensus on anything. So I have to figure out a rule for solving these problems. And the rule that we have in Bitcoin is actually, again, a very simple and elegant rule. It's the consensus rule of Bitcoin. And what it says is that, okay, temporarily I have two different valid chains, that's fine. And the miners can actually choose. The miners can choose to extend each one of these valid chains. Okay, so if you are now the miner, you're a miner and you're working on creating block n+1, you can choose which variant of block n you want to work on. You can basically choose the pointer that you have in your block that points to the previous block. So you can point to this one, or you can point to this one. So miners get to choose. But of course, miners choosing will just continue the chaos, right? So miners get to choose which block to extend or which chain to extend. But now here's the genius part. As soon as one chain gets longer than the other chains, the longest chain is always the consensus chain. Okay, so I'm going to write this one in all caps for you, because if you just remember one thing from this course, it's that the longest chain is the consensus chain. Okay, so I have a fork like this, that's fine. I have two valid blockchains now. But then at some point, someone will extend, someone will add the next block. Let's say I'm unlucky, and let's say both of them get extended at the same time. Okay, maybe they even get forked even more. Maybe I get even something like this, right? So at this point, I have 3 valid blockchains. But this cannot continue forever. At some point, and again, I'm not going to do the probabilistic analysis of this, but with probability 1, at some point, one of these chains is going to get longer than the others, right? So at some point, for example, I will have a situation like this. Someone adds a block here, and now this chain, the chain that starts from B0 and goes like this is longer than all the other chains. So now this is the consensus chain. All the nodes drop all the other chains that they have, and they get back to the consensus chain. So now, I know I'm running out of time. I have to just say one more point here. I said something here that was kind of a lie. I said a node keeps track of the blockchain, but actually a node keeps track of all valid forks of the blockchain. Forks of the blockchain. So if I have a situation like this, if I have a fork, all of my nodes will keep track of both branches, right? And basically simulate each branch separately. And as soon as one branch gets longer, they drop the shorter branches. Now, I know that with probability 1, there would be a branch that eventually gets longer than all the other branches. So I'm sure that with probability 1, everyone will reach consensus eventually. In practice, usually when there is a fork, we reach consensus in 2 or 3 blocks. So yeah, this is how Bitcoin works. This is how a decentralized ledger works. We get consensus on the blockchain, but we don't get consensus at all times. Sometimes we have a fork. And if we have a fork, it takes us a little bit more time, but eventually we get back to consensus. Okay, that's it for this session. I'll see you next